A ball rolls off a desk at a speed of 5 meters per second and lands 0.5 or 1/2 seconds later. It's interesting that 0.5 seconds is plural. Anyway, yes, makes sense. How far from the base of the desk does the ball land? How high is the desk? And at what speed and angle is the impact? Okay, so first thing I do is I draw a picture. Maybe if you're better at visualizing things and you're really smart, you won't have to. But I am not, so I draw pictures. So we have a ball, comes off at 5 meters per second, goes kind of like this, and it lands 1/2 seconds later on the ground. So this is a kinematic equation in 2 dimensions, and so we're going to use the kinematic equations. So first thing you do, draw a picture, and then second thing, if you know what equations you're going to use, you write them up. So I write them up like this. A equals A. What I'm saying there is just that the acceleration is constant, which is one of the requirements for these kinematic equations. You might not know how to drive these if you haven't taken calculus yet, but if you haven't taken calculus, you just memorize them. So V equals AT plus V naught. X equals 1/2 AT squared plus V naught T plus X naught. And the reason I write them in this order is it relates to their derivation. And it's easy to kind of keep them straight when you do it that way. Again, if you haven't taken calculus, this is kind of a mystery to you. But if not, then memorize. Okay, so these are equations. And even though I wrote x here, it doesn't necessarily mean the x dimension. It can apply in any dimension. In this specific case, we're going to use it for x and y. So first thing we're going to do is how far. I'm just going to try and do them in order. I think we could do them in pretty much a different order, but we're going to do them in order. So how far from the base of the desk does the ball land? So what I'm going to call that is, I'm going to say it lands a distance of x final away from where it starts. So we know how long it's in the air. So we're just going to use, I'm going to do x dimension, right here. Probably should have put the little colons over here. It's okay. And the equation we're going to use is this bottom one here. So we do x equals 1/2. This will be x final. 1/2 AT squared plus V naught T plus X naught, where X naught is the initial distance. So we're going to write up what these variables are. So we're going to start with X naught. So we're going to say it starts at 0. The initial velocity, they gave us that already. It's 5 meters per second. And that 5 meters per second, we're going to assume that this is a horizontal desk. If it was kind of a funny shaped desk, it would be different. But we're going to assume that this is horizontal. And so that the 5 meters per second is completely in the horizontal direction. So let's say 5 meters per second. Acceleration, there's 0 acceleration in the horizontal direction. Acceleration in this case only works downward due to gravity. And we'll say that time equals 1/2 seconds. So, yeah, it seems reasonable. So the only thing we don't know is x final. X final equals question mark. So x final equals, we'll do the 1/2 times 0 times 1/2 squared plus initial velocity, which is 5, times time, which is 1/2, plus initial distance, which is x naught, which is 0. I just rewrote this equation up here with these variables plugged in. Looking at it again, get my canceling. So this has a 0 in it, so that goes to 0. X naught is 0, so that's 0. So the final distance traveled in the x direction will be 5/2 meters, which is about 2.5 meters. Okay, got that part. So now we want to do how high is the desk? Or I'm going to rephrase that, how far does the ball fall? And we're going to again use this will be the y dimension. We're going to use this same bottom equation right here. So I'm going to say that y final equals 1/2 AT squared plus V naught T plus Y naught. And in this case, I just replaced the x's with y's. That way it kind of emphasizes that we're doing this in the y direction. Minimize confusion, avoid human performance traps. Also, if I wanted to, I could write down here that this is initial velocity in the y direction, and this is acceleration in the y direction. That gets a little bit messy, so I'm just going to leave that as assumed. But keep in mind that this acceleration here is not the same as that acceleration up there. Different directions, dimensions. So acceleration equals negative 9.81 meters per second. You can use 9.8, that's fine. Initial velocity in the y direction will be 0 because it's going up horizontally. And initial height, we don't know, but we do know the final height, which is 0. And you could also say that the initial height is 0 and the final height is actually some sort of negative number. Either way, I like it this way though, saying that the ground is 0. But there is some flexibility there in life. Okay, and then let's see, do we got everything? Oh, and time equals 1/2. Way off to the side, 1/2. Yes. Okay, so then we plug things in. Bum, bum, bum. Run out of colors that I like. Looks like dark green. I want to do dark green. Okay, so plugging everything in, y final 0 equals 1/2 times a, which is negative 9.81. You can just do 9.8, but then I feel bad about using just 9.8 when I can be more exact. 1/2 squared, because that's time. Initial velocity, which is 0, again times the time, plus the initial height, which is just y naught, because we don't know what it is. Okay, this goes to 0 because it's 0, and we're left with 9.81 negative divided by 8, because 1/2 times 1/2 times 1/2 is 1/8, plus y naught, and therefore y naught, or y initial, or y0, equals 9.81 divided by 8. Yeah, I can't do that in my head. So I'm going to use my calculator. On clear, 9.81 divided by 8, click, we get 1.23. I'm going to say 1.23. 1.23 meters is the initial height. Okay, so we got the first part done. So we got the first part done, check. That was 2.5. We got the second part, which is 1.23. What is the speed and angle of impact? You know, that's kind of like 4 questions. Okay, we can do this. Okay, so the speed is going to be the magnitude of the combined velocity. So what we're going to do is when this hits, I drew it hitting perpendicular. It's not. It's going to hit something like this. We're going to have some velocity in the x direction. Oh, and we're going to have some velocity in the y direction. We're going to make a triangle, use Pythagorean's theorem, and from there, we'll find both the angle and magnitude. So I'm going to do it up here because here's some white space. Purple, red. Ooh, red. So now, first time we used this equation twice. For the first 2 problems, we used the bottom equation. Now, for this problem, we're going to use this equation right here. Yes. So we're going to start with finding velocity final in the x direction. Now, since there's no acceleration, we can look at this and be like, all right, acceleration is going to be 0. Time doesn't matter because acceleration is 0. And so velocity final will be velocity initial, which is 5 meters per second. Not too hard, did it? All right, velocity final in the y direction, using this equation, will be acceleration, which will be 9.81 times time, which we know is 1/2 seconds, plus velocity initial, and we know the initial velocity in the y direction is 0, so that'll be 0. So I'm going to write this as 4.9 meters per second. So 4.9 is 9.8, I just ignored the 1, divided by 2. I just know that off the top of my head. I guess you could kind of figure it out. And I just ignored the 9.8, the 1 on the 9.81 because convenience. Okay, so now we have a triangle that looks like this. So we have 5 meters per second going that way, and we have, adding vectors tip to tail, 4.9 meters per second going this way. Add them together, and so speed total, does that work? So squared will be 5 squared plus 4.9 squared. So I can go back to the calculator. 5 squared plus 4.9 squared. It gives us like 23? No, 49. Second square root, second answer. And we get 7. Wow, that is really close to 7. 7 meters per second. Okay, so now we need to know the angle, and the angle will be probably a little bit less than 45. So for the angle, we do SOHCAHTOA. This is how you find, this is your mnemonic. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, which is the one we want. So we know that tangent of theta, which is the angle we want up there, equals opposite, which is 4.9 over 5. Therefore, theta equals arctangent of 4.9 over 5. So we're going to do 4.9 over 5. Check. Second arctangent. Second answer. Click, clack. We get, I don't want that. So mode, degrees. Yes, I want it in degrees. Can I just hit enter and do it again? That might be the right answer. I'm going to check it again just to be sure. So 4.9 over 5. I think that seems right. 44.42. Yes, I believe that. 44.52. 44.42. Which makes sense because these 5 and 4.9 are pretty close. So it's almost going to be a 45-degree angle, but not quite, slightly shallower. 44.42 seems like a reasonable value. Okay, so let's backtrack, make sure we got everything. What is the speed? The speed is the magnitude without direction, which is 7 meters per second, and the angle of impact is 44.42. And that's an angle with respect to the horizontal, so going down. Yeah, I'm good with that. So to backtrack, kind of recap what we did here. We had a ball falling off a ledge, which assumed it was horizontal. We had an initial velocity of the ball going straight horizontal, which is convenient. We found the x dimension of how far it went using our third kinematic equation right here. We then did the exact same thing to find the height, how far it fell, using the same kinematic equation, but in the y dimension instead of the x. And in the y dimension, we had an acceleration, gravity, 9.81 meters per second squared. And then we wanted to find out the speed, and so we used our second kinematic equation right here. We knew the horizontal speed, 5 meters per second, it was constant the whole time, no acceleration. And then we had an acceleration in the y direction, so this equation was slightly more complicated, but not that bad. And we found out that it was 4.9 meters per second. We then used vectors and SOHCAHTOA to then find the magnitude and direction of the final speed. So that's how I would approach this problem. Hope that helped. See you next time.